Assalamualaikum and welcome to the video. I am Muhammad Hafizul Hafiz bin Husin from Physics Unit KMPK. In this video, we are going to go through Experiment 2, Free Fall and Projectile. What we hope that you get from this video is that you can appreciate the importance of the practical session in facilitating your learning of physics, hence making the learning meaningful. Because some of the apparatus might be foreign for you, we introduce them in the video. Reading the procedure with no background knowledge could be confusing and intimidating. So we go through the setup process for you, and we hope the procedure will make more sense to you. We are not going to go through the procedure step by step, but rather we are giving you the overview of the experiment and some useful tips to help you with the experiment. Make sure you have your lab manual and jotter book with you. You are going to need your jotter to jot down important information and tips as you follow along with the video. Before going to the lab session, make sure you have the objective, a brief summary of the procedure, table for data collection ready in the jotter. You can also add sketches as a visual tools to help you to visualize the procedure better. It does not need to be perfect or beautiful, you can just keep it loose. Free-falling object and projectile only has gravitational force acting on them. Hence, in both of the motion, the object will accelerate. The object will accelerate with the gravitational acceleration. In this experiment, we are going to utilize this concept to look for the value of the gravitational acceleration. Open the manual and go to the figure 2.1 in the manual. Look at how the falling height is drawn in the diagram. The falling height is measured from the trapdoor to the steel ball. Free falling object can be described by using the quadratic equation S equals to ut plus half at square. As the ball is released from rest, the initial velocity of the ball is 0. The ball falls through the height h, so the displacement of the ball is taken to be negative h. The ball accelerates downwards with a gravitational acceleration. Thus, the acceleration of the ball is equals to negative g. The displacement and acceleration of the ball is negative because they both are vector quantity. The sign indicates the direction of the vector. Substitute all this value into the first equation. We have negative h equals to half gt square. We can cancel out the negative on both sides of the equation. This will leave us with h equals to half gt square. To see how the manipulated variable, the height, affect the time, the responding variable, we will plot them in a graph. From the equation that we have established earlier, we can plot the height against the time square. If you compare the equation with a straight line equation, the height will take the y-axis, the t-square will take the x-axis. The value of c is 0. The graph should start at 0 and the graph is going to be a straight line graph. When plotting your graph, make sure the graph occupies at least 80% of the graph paper. Coming back to the straight line, the gradient of the graph will be equal to the half of g. Choose 2 points along the line and draw a right angle triangle connecting the 2 points. Make sure the size of the triangle is at least 50% from the size of the graph. The gradient of the line can be calculated using the equation m equals to y2 minus y1 over x2 minus x1. The value of gradient will be equals to half of g. Arranging the equation, we get g equals to 2m. you are going to compare the value obtained from the experiment, which is from the graph, with the theoretical value of the gravitational acceleration. Before we continue with the procedure, I want you to pause the video, open the manual, and go to the procedure section of the experiment. Read through the procedure. After you have read through the manual, you can come back again to the video. Hi, welcome back. If you have read the manual, these two statements will make a lot of sense to you. In this experiment, you are going to manipulate the height and then record the falling time. Finally, before going to the apparatus and setup video, we are going to present to you with the table for data collection. Repeat each set at least twice and then find the average. Make sure you enter the uncertainty for measurement. In the measurement column, make sure you write the calculated value of t squared in standard form and write the exponential power in bracket if present. Let's go to the apparatus and setup. We are going to use digimeter as the timer to record the falling time. This is the power button. The timer has an input A as a start trigger. We are going to use these two input jack. And then we have input B. Input B is the stop trigger. We are going to use these two input jacks. Your reading will be displayed here. This is the function button. To start using the timer, we switch on the timer. Press the function button and go to start and stop. The reset button will reset the timer back to 0. This is the electromagnetic holder. It is used to hold the steel ball. To attach the steel ball onto the holder, press the top and attach the ball at the bottom. To release the steel ball, just press this button, the metal button at the front of the holder. Next, we have a trapdoor and we have a white circle on it. You need to make sure that the ball falls inside of the circle. It has two output jacks. This is the close-up view of the trapdoor. We also need a retort stand. The electromagnetic holder will be connected to the input A of the timer into these two input jacks. The trapdoor will be connected to the input B into these two input jack. And make sure you set the function to start and stop. This is the holder. You are going to attach the steel ball to the holder. And you are going to secure the holder to the retort stand. Take the trapdoor and place it right under the holder. This cable is used to connect the holder to the timer. One end of the cable is connected to the holder and the other end of the cable is connected to the input A of the timer. Like so. The next pair is used for the trapdoor. Connect the cable from the trapdoor to the input jack of input B. Like so. When you release the ball, make sure the ball falls onto the white circle. The falling height is measured from the trapdoor to the steel ball. You are going to vary the height and measure the falling time. When you release the ball and the ball hit the trapdoor, the timer will give you the falling time. To clear the time, just press the reset button. For each height, you are going to repeat the experiment at least twice and record the observation in the table. That is it for this experiment. Thank you for your attention. Now, we are at the second part of the experiment, the projectile. The diagram 2.2 is the setup diagram. We are going to look at the diagram carefully. We start with the small h. The small h is the release height of the steel ball. You are going to manipulate this value in the experiment. As you go down, we have the capital H. The capital H stands for the falling height of the projectile. This height is going to be constant throughout the experiment. The capital R at the bottom is the range of the projectile. You are going to measure R from the pendulum bob to the point where the ball lands on the floor. The pendulum is used to mark the end of the track to the plywood. As the ball is released, the ball is rolling on the track. It has both translational and rotational kinetic energy. From the principle of conservation of energy, we have this equation. mgh equals to half mv square plus 1 over 5 mv square. The 1 over 5 mv square is the rotational kinetic energy of the ball. At the end of the track, the potential energy is transformed to the kinetic energy of the ball. The h in the equation is referring to the release height of the steel ball. The m can be cancelled out. This leaves us with the equation gh equals to 1 over 2 plus 1 over 5 times v square. Rearranging the equation, we get h equals to 7 over 10 g times v square. The range of the projectile can be calculated as follows. R equals to the horizontal velocity of the projectile times the falling time of the projectile. R equals to v times t. Because we are only dealing with horizontal projectile, velocity of the ball at the end of the track is equals to the horizontal velocity of the projectile. We can substitute equation of v in terms of r and t. This leaves us with the equation of h equals to 7 over 10 gt square times r square. The value of t square can be obtained from the extrapolation of the graph free fall. Same as before. To see how the height affects the range, we will plot them in a graph. From the equation that we have established earlier, we can plot the height against the range square. If you compare the equation with a straight line equation, the height will take the y-axis, the range square will take the x-axis, and the value of c is 0. The graph should start at 0, and the graph is going to be a straight line graph. When plotting your graph, make sure the graph occupy at least 80% of the graph paper. Coming back to the straight line equation, the gradient of the graph will be equals to 7 over 10 gt square. Choose 2 points along the line and draw a right angle triangle connecting the 2 points. Make sure the size of the triangle is at least 50% from the size of the graph. The gradient of the line can be calculated using the equation m equals to y2 minus y1 over x2 minus x1. The value of the gradient is equals to 7 over 10 gt square. Rearranging the equation, we get g equals to 7 over 10 mt square. You are going to compare the value obtained from the graph with the value that you get from the free fall experiment and the theoretical value of the gravitational acceleration. The t square is the falling time square of the projectile. To get the value of t square, you need to go to the free fall plot, mark the falling height, and then you are going to extrapolate the graph to get the value of t square. The value of the time square that you get from the extrapolation is the falling time square of the projectile. you are going to substitute this value into the equation of gradient for the projectile. Before we continue with the procedure, I want you to pause the video, open the manual and go to the procedure section of the experiment. Read through the manual. After you have read through the manual, you can come back again to the video. Hi, welcome back. If you have read the manual, these two statements will make a lot of sense to you. In the experiment, we are going to manipulate the release height and we are going to measure the range. Finally, before we go to the apparatus and setup video, we are going to present you with the table for data collection. Repeat each set at least twice, find the average, make sure you enter the uncertainty for your measurement in the measurement column. Make sure you write the calculated value of r square in standard form and write the exponential power in bracket if present. Let's go to the apparatus and setup. The first apparatus for the experiment is the curved railing track, the soft board to catch the falling steel ball, a plasticine to secure the end of the curved railing track to the table, a white drawing paper. We are going to use the white paper together with a carbon paper in order to locate the position where the steel ball hits the floor. This is the carbon paper. And then we are going to need a string and a bob to make a pendulum. Place the flat end of the track at the end of the table. I'm going to show you a little trick that you can do to make the measurement of the range a little bit easier. Fold the white paper in half. As you open the fold, you will notice a crease line in the middle of the paper. You are going to use this line as a reference when measuring the range of the steel ball. Stick all the four corners of the paper to the board. This will prevent the paper from moving around, and we slide the board toward the edge of the table. In an actual setting, you are going to place the board on the floor. The end of the curved track is fixed to the end of the table with a plasticine. A pendulum is then placed under the track to mark the end of the track on the board. Make sure the pendulum is straight when viewed from the side and the front. We are going to adjust the board so that the end of the paper sits exactly under the pendulum, and the pendulum is perpendicular to both ends of the paper and the crease line on the paper. The falling height of the projectile is measured from the board to the end of the track. This height is going to be constant throughout the experiment. The steel ball will be released from a different height on the curved railing. Mark this position on the curved railing. Place the ball in between your highest and lowest point on the track. Release the ball and observe where the ball lands. And then place the carbon paper about this position. For each height, you are going to repeat the experiment 2 or 3 times and check for the consistency of the reading. Repeat the set if necessary. You are going to measure the range of the projectile by referring to the fold lines.